So the second lecture, we're going to talk about building on the idea of distribution and variation that we talked about in the previous lecture. And we add a co-variation in front of it, so which means that we'll be moving on from a single variable to the relationship between two variables. And I haven't changed the date on the slides. And today is May the 21st. So a quick review of what we have been through. We talked about quantitative data. And it is really any data that's in numerical forms that is quantitative data, and any data is in non-numerical forms are qualitative data. So if some of you work with data such as text or image or video recording, and those are qualitative data. So the interesting thing is that the qualitative data nowadays can be visualized and presented using quantitative transformation behind it. So this is a common, what I'm presenting on the screen is what I did in the March 24th with a bunch of level 4 undergraduate students of the same question that I've just asked you guys. And so this is a word cloud, I think. So this is a visualization of text, right? And any visualization involves mapping of some kind of a quantitative feature of the text to a aesthetic dimension. So in the cloud, in the word cloud, the size of the text is probably correspond to the frequency of which a word has been mentioned, right? And so you can see that this is the result. This is a way of presenting the results of a simple qualitative questionnaire. And you can see that back then in the March 24th, a lot of people were saying that they're anxious and stressed and bored, scared, worried, tired. So say if you want to do some kind of comparison, we can look at our data from the Mentimeter, which I'm about to share with you. Give me a second. So yeah, this is your results, right? And so if you compare it to, let me just put it on side to side and share the whole screen with you so you can compare it. Share my desktop. So you can see these are to the right are your results, and to the left are the students' results, if you can see them. So it seems like nowadays people are more tired, still stressed, but we're seeing more, some of you are overwhelmed, but we're also seeing that people are feeling more okay now, more bored than stressed, judged by the size of the terms. So we have 15 participants in this case, and some people even feel happy. So really, this is just okay. I have to go back and share the PowerPoint slides. Again, this is just Zoom, but this is just Microsoft Teams. So if you do some kind of analysis, this is how it would be done with qualitative data, right? But nowadays, qualitative data can actually, there are many ways of quantifying them, especially for text data. So this is an example of in natural language processing, they would turn sentences into what they call count vectors. So they turn in these 3 sentences into a matrix, right? So a terminative matrix, you can see each column represent a single word, like I, like, enjoy, and in the data seems to represent how many times they have appeared. And you can also see a little bit of a covariation data, because I and like co-occurred 2 times in this whole matrix, right? So in those sentences. So this is count vectors is a one way of turning text data into vectors and then into quantitative data, and then can be further processed. And due to the development of computation power, this has become more and more available for just everyday, like regular researchers. Doesn't require like a supercomputer or anything anymore. So another kind of quantifying text data is so-called word-to-vec. So this is one. You can see that this is basically turning different words, representing their meanings in vectors. So, I mean, this is a whole theory of what is of distributional semantics behind this, defining the meaning of a word as in terms of the word that are most likely to occur with the word in the big corpus of text. So what we're seeing here is that there are 4 dimensions that are extracted from these meanings, and they call these dimensions animal, domesticated, pet, and fluffy, and these are completely subjective, and these are completely arbitrary terms that people these are represent people's explanations of these dimensions based on the results, right? So dog scores lower than cheetah, for example, on animal dimension, which cheetah is more like an animal than dog, for example, and how much they are domesticated, and how much they can be used. They are pets, perceived as pets, and the fluffiness, right? So this is not really exact, and might actually contradict some of your understanding of what pet is. And again, these dimensions are just named completely arbitrarily and based on the semantic meaning of the word sometimes. But this is another way of turning words into certain dimensions, and based on these numeric dimensions data, dog have 4 values on these 4 dimensions, and these can be further analyzed and can be used for all kinds of analysis, such as a sentiment analysis, or natural language production, all kinds of stuff, all based on this kind of vector data. And these are just 4 vectors, 4 dimensions, and in the big data set, they will have thousands of dimensions for every single word. A quick review about data set, right? So, and this is a little bit different from the previous lecture. So in the data set, you've seen it in Excel data set, we've seen it, it's just a bunch of observations and organized into variables. An observation is just a data obtained at a specific occasion on a particular subject. A variable is a feature or characteristic of these subjects, okay? And the variables can take different values, which is quite important. So this is the data set that in our Excel file, if you go to the first sheet, I believe it's called region mate 16. And you can see each observation comes from an area or region, okay? And each variable name, which goes on top of, which is the first row, is the variable names, represents some kind of a feature of these areas, of these regions. So you have area code type, which they are the same, all region, a date, and cumulative lab confirmed cases, and also added some variables such as the population in 2019 and the density measured by people per square kilometer of each region. Okay? I'll come to that later. We also talk about the idea of variation or variability. These are just 2 terms that I use interchangeably. Variation can happen at the same time across different individual subjects, or it can happen across time when the subject changes. So, but here's something that's important that I kind of mentioned, but I didn't really go deep into in our previous lectures. But understanding statistics or statistics reasoning is really to understand, first of all, how data is produced. But the most importantly is to understand that there's variation everywhere. Okay, and also the analysis is basically how to quantify and explain this kind of a variation that occurred in nature. So we talked about two different types of variables in terms of arithmetically. So there's categorical variable, which takes category labels, and they can be used to put a subject into groups. Okay, and the codes like 0, 1 or 0, 1, 2, 3, 4, even they look like they're arithmetic, but they don't have any arithmetic meaning, which means that it doesn't make sense to add them, to subtract them, or to compare them based on these codes. So these codes are just indicates group memberships. In comparison, quantitative variables, they take numerical values. These values usually are the results of some kind of a measurement. And you can add or subtract or multiply, divide, or compare magnitude on these values. Now, there are different levels of measurement, which we'll mention later. So not all levels of measurement will allow you to do all these things listed here. Okay, so it depends on the level of measurement. You will be able to either compare magnitude, or you'll be able to compare multiply or divide. So again, so if you look at the data again, you will see some of the variables are a categorical variable, such as area code. So the area code is just a string letter followed by some numbers. They don't really have any kind of a numerical meanings. They just, other than categorizing, identifying the different regions. But we can also see the lab confirmed cases or population are quantitative variables, and you can actually compare the magnitude, or you can also say an area of 5,701, which is London, which is quite crazy, has more than 10 times of density than Northwest, right? So you can make these kind of claims about magnitude or ratios, and they make sense. So in terms of research design, we mentioned two types of variables for now. One is the independent variable, which is the cause or the factor that is explaining the variation in the other factor. And dependent variable is the effect or the factor that is to be explained, right? So again, what's being explained here is the variation or variability of the dependent variable. We also talked a little bit about some very basics of research design. All research design can be basically categorized into two broad categories. Experiments, right? So experiments basically involve some kind of a manipulation of the independent variable. So by manipulation, I mean creating groups, creating conditions that represent different levels of the independent variable. The dependent variables are then measured. So the experiments are specifically randomized experiments are the only way to establish true causal relationship. This has been agreed by a lot of the classic statisticians or researchers. Nowadays has been challenged a little bit, but still, mostly the consensus is that randomized experiments, is the only way to test and establish causal relationship. And therefore, like a lot of researchers who do experiments tend to emphasize that a lot, because they'll be saying, hey, you can analyze data, but in order to actually test causal relationship, you need to do experiments, randomized experiments. The other category is correlational. I call it correlational. Basically, you measured IV and DVs, and usually at the same time. And you can do it across different times if you have a longitudinal design. But we're not getting there at the moment yet. And the causal relationship, because IV and DVs are measured at the same time, then there's no temporal difference of, like an experiment, you manipulate IV and then you observe the DV, right? So in the correlational study, you don't really have that. So it's usually determined by a theoretical plausibility. So what is deemed theoretically plausible to have one variable as the dependent variable or the other? So we talked about exploratory data analysis. It's basically depicting or describing a single variable or the relationship between two different variables, or more than that. So we talked about how to describe the data using graphs, a single variable using graphs. And we can also do that using numbers, which we will be talking about today. We can also explore the data for patterns, which we will talk about today as well. Okay, we kind of did it last time as well by talking about distribution of a single variable. But today we'll also address how to depict a relationship between two variables. Something to mention is just mentioned the experiments are the only way of establishing causal effects. So, and these are the particular conditions in which causal effects can be established, right? The first is the IV and DV need to co-vary. So the changes to the IV results in change in the variation of the dependent variable. The second is that there should be a temporal difference between the manipulation of the IV and the observation of the DV. The third is that the other factors has to be controlled for. So which means the confounding variables, which we will talk about at the end of the course, so-called confounding variables, which means external factors, unwanted factors that might have affected the DV, they have to be controlled for. The fourth is that there have to be a logical explanation about how independent variable influences dependent variable. Okay, plausibility. So we talk about distribution. So distribution is defined as what values a variable can take and how often it takes these values. And they can be depicted by histogram, for example, right? They also can be depicted by statistics. So for a categorical variable, we can use these kind of simple charts. But for a quantitative variable, we'll be using histogram to depict the distribution. And another thing about histogram, the x-axis represents these intervals that are ordered from smallest to largest, okay? And the y-axis is the frequency. How frequent do data recur within each interval, right? So how many observations are there in each value interval? So we'll build on that, and in today's lecture, we'll talk about numeric descriptions, or you can call it descriptive statistics. And we'll also talk about how to depict the relationship between two variables, or the idea of covariation. Okay. So before we do that, it's important to mention something that is important throughout this course, and it's actually very important for understanding statistics, is that first of all, the data we were talking about is the sample data, and it's usually taken as a subset from a larger population. So we want to draw conclusions about a population, but we only have access to the sample, right? And so this is basically how data is produced, is that it involves measurement and it involves sampling. So in the statistics, they usually talk about two types of statistics. One is the sample statistics, and the other is the population. They don't call it statistics, they call it population parameters. So this distinction is both theoretically and practically important. So and it is a distinction that will keep happening during today's lecture, and it's important to keep in mind which one is which. Basically, sampling statistics is what can be calculated and what is usually calculated from a discrete number of data points of values within a sample. And population parameters are usually being it's more hypothetical, it's more theoretical, right? It's more like mathematical assumed. So we're using sample to try to estimate the population, right? And then we can use what we know about probability to model how close we are in a sample, right? By in terms of estimating the population and the risk and error involved doing this kind of estimation. So, okay. So come to describing distribution with numbers, right? So numbers are more precise, right? And they're also more definitive. You can have a graph that looks kind of like all over the place, or but you have one single number, right? And most importantly, the numbers can be used in analysis. And there are two types of numerical descriptions of distribution. Okay, one is center or central tendency, or the other is spread or dispersion. So here are two histograms. If you these are histograms, and you can see that the idea of center is basically where is the center of the entire distribution, but the spread has to do with the range. Okay, so the distributions can have the same kind of center, but then they can have very different spread. Okay? And the measures of center or central tendency basically describes the typical value of a variable. Okay, so there are the three most popular measures. The first one is the mode, and then there's the mean and the median. Okay? And each of them is based on a different kind of idea of what typicality is. So the mode is the most frequent value within a variable. Okay, and so for example, in this example, if you have the numbers of goals scored per game can vary from 0 to 8. Okay, and if you're a football fan, probably know what that 8 comes from. And we have a very small numbers of set, right? A small number of values in the set from 0 to 8, and you have a lot of frequencies. Like these small numbers, each number in the set happens quite frequently, right? So you can see that the mode here will be 2, right? Because 2 occurred 51 times is the most frequent number. So we can say the mode for this particular data is 2. So that's straightforward enough. But mode is most useful when, first of all, for a particular kind of data set, the data can only take a small set of values, and there's a large numbers of occurrence per value, such as in our example of total goals per game. And also you can see that the mode is really unaffected by extreme values. So if you have another game where they've scored 9 goals in total, the mode is still 2, because unless another value catch up in terms of frequency. For example, if there are another 6 games where they scored only 1 goal, and 0 games scored 2 goals, and then they can catch up, right? And the 1 is not even extreme value. So it's largely unaffected by the extreme values. So, but the mode in the histogram is a little bit tricky, right? So first of all, it is quite if we have a quantitative variable, it's a little bit more difficult to talk about mode, especially if the value can take very large numbers of, if the variable can take a large number of values. So in this case, this is the histogram we did in previous lecture, and this is the number of cases in each upper tier local authority. So we can see that, and we binned again on the histogram on the x-axis we have intervals, right? So and that kind of reduces the numbers of values for the data. Otherwise, it can go from 0 to 5,000, and there are 5,000 different values, and it doesn't make much sense to talk about mode there, right? But if you started to turn these into intervals, mode starts a little bit make more sense. And in this case, the mode is just the one that is tallest. So the mode is between 500 to 749. It occurred more than 45 times. So there are 45 to 50 local authorities, upper tier local authorities in England, had coronavirus cases number from 500 to 750. Now, it's not exact value, right? So there's no exact value in it, but the mode is now in a way that's it's like an interval now. Okay, so in histogram for quantitative variable, it makes more sense to talk about mode when you have histogram, and again, it's very visually salient. It's just the tallest column in a histogram, but in this case, it doesn't represent a particular number, but a group of number, a range of number that is most frequent. Okay. The second is the mean. The mean is just the average value. It's very easy to understand. Again, this is the questions that you've answered in the previous lecture on the Mentimeter. And you can see that the numbers in the middle are the mean values, right? The average of all of your responses. And on top of the mean, again, this is a neat feature of Mentimeter. You can see the kind of distribution, right? Some kind of histogram, but a smoothed histogram of all your responses, right? Those shades. And again, I put the same question there twice, and you got two different values. One was 5.5, 5.7. But the mean, the important thing to talk about mean is that there's sample mean and there's population mean. And the sample mean is usually called the average, and they're calculated from a discrete set of numbers. So it's the sum of the values divided by the number of values. It can be calculated quite easily. But the population mean is what we call expected value. Okay, it's what we're trying to approach with our sample mean, right? We're trying to estimate population mean using a sample mean. So it's like a theoretical concept that's out there, and we're trying to get closer to this population mean, but never can. But we can kind of using math to assume what the value is, or sometimes we know what the value is. And in this case, population mean, like more precisely speaking, the population mean is the measure of the central tendency. Okay, so the central tendency of a random variable. We talk about it we'll talk about random variable in the next few lectures, which is a very important concept in statistics. But just the point here is that we differentiate between sample mean that can be calculated using a sample data with population mean that is the mean that's out there. We know it's out there, and we're trying to get close with the sample mean, but never exact. Okay. So the equation of arithmetic mean is quite simple. You sum up all the scores, all the values, and divide the sum by numbers of values. Okay, and again, these are some. I'm showing some equations here. I'll explain to you a little bit more for those who are not familiar with these math equations, what they mean, and I hope that you get more familiar with these terms such as x bar, like x with a bar on top, xi with an I as a little I, or sigma I equals 1 to n divided by n, and n. These are the mathematical symbols that you will be seeing quite frequently in the upcoming lectures. So that's that. So You can also calculate arithmetic mean if you have the frequency table and you have a small set of variables. So in this case, you have all the frequencies, and in order to calculate the number of goals scored per game, average number of goals scored per game of 192 games, you're basically calculating the sum by first of all multiply the goals per game with the frequency, right? And then sum them together. And then you can also sum all the n's together. It was just 192. So, okay, so it's important to remember these are not the data set contains 192 observations. Okay, it's not 9 observations. So the mean average goals scored per game is 2.36. Okay. So this is just one way of how it's calculated from a frequency table, that you have a discrete set of values that this variable can take. And one thing to point out is that it's quite sensitive to outliers. So in this sense, it's quite different from mode, right? So mode we saw earlier is insensitive to outliers. But here, let's see if we have another game, just single one game. So remember this 2.36 is based on 192 games. But if we have another game where they score 20 goals, which happen in some international games where, you know, 2 different levels of teams play each other. So if you have a game where there are one game where they score 20 goals in total, then your mean will actually change from 2.36 to 2.45. So considering that this is 1 on top of 192, it is quite a you get the idea, right? So it is quite sensitive to large outliers, in this case 20. So just something to be keep in mind, right? So because a lot of the analysis actually is based on mean, it is very important to screen for outliers, especially for those who outliers caused by mistakes. So for example, one common mistake people make is sometimes people use 99 as the code for missing value. But if you forget to account for that and just treat 99 as a value, then it will change the mean, right? So the median is the midpoint that separates the higher half from the lower half of a variable. Okay, so for a discrete set of values, which is sample from our sample, in order to get the median, you can just order the data from the smallest to the largest, and the median is just the middle value. So it works a bit different when the n is even or odd. So if there are 7 values in the entire data set, then yeah, you have a middle point usually, right? But if you have 8 observations, like 8 values in the data set, then you have to calculate the average again between 2 values that are in the middle. Okay, so that's just like a little bit practical differences depending on the number of observations you have. But theoretically, it separates the upper half from the lower half. So it's the value that divides the entire distribution, right? 50-50. And we talk about skewed distributions. And again, these are histograms that depicted a skewed right distribution. And in this case, the means is usually located to the right of the median. Okay, so the median tend to be to the left of the mean. So that's why another reason why it's called skewed right distribution, because the position of the mean is usually to the right of the median. And for skew left, again, the mean usually to the left of the median. Okay. And notice that although the most salient spot on the histogram is usually the mode. The median and the mean are both not even they're close to the mode, but they're not the mode. Okay. So another thing that you should keep in mind when you look at histogram, because I don't know, like even for me, you're looking at a histogram, you got immediately attracted to the tallest spot, right? And you tend to think that is where the mean is. And the truth is that mean is usually somewhere on that slope, but it usually is not. Usually, it's not the mode where the mode is. Okay, so we'll talk about measure of spread, then we'll take a break, and then we'll come back to actually do the worksheet. So the measure of spread described the dispersion within a distribution, okay, of a distribution. So you have range, you have interquartile range, and then you can have a standard deviation, which we will do on the worksheet. So this is one way of looking at range. So the range is really the minimum to the maximum. And the m in the middle is the median. And the median divided the data into 50-50 and quartile 1, or the first quartile, further divide the first 50% into 25% and 25%. So at the third quartile divides the upper 50%. So the interquartile range is the third quartile minus the first quartile, right? And so yeah, interquartile range contains the middle 50% of the data. And to depict the spread, we can do something called the box plot, or its longer name is called box and whisker plot. So what the box and whisker plot does, it is that it utilizes a 5-number summary of a distribution, including the extremes, minimum and maximum, the quartiles, quartile Q1, 25% quartile, the third quartile is 75% quartile, and the median. The box in the middle is boxed by these quartiles, and there's a line in the middle, which is the median, and the whiskers are defined by the extremes. Let's do a quick exercise before we move on, which we will make a box plot in Excel. And the box plot again is a very simplified way to depict the distribution of a variable, right? And so we'll try to make a box plot on Excel, and then we'll take a break. So let me going to share my, okay, let me just do a little bit of cleaning here. Okay, so Excel file. I'm going to share the Excel data file with you. Okay. Share. I'm going to just share this whole screen with you, actually. So now you can see my screen. We're trying to make a box plot in Excel. Okay. So this is the data that we had, and this is the region on May 16th. So, but region only have 9 observations, so that might not be enough for, a little bit too small for to call a distribution, and it's a categorical variable. Well, it's not a categorical variable, but there's not enough observations there, right? So let's go to upper tier May 16, and let's say we want to make a box plot of the cumulative lab confirmed cases up to the 16th of May. And this is quite straightforward. You just insert one of it is the box plot recommended charts. Where is the box plot? Okay, let me think about it. Box plot, box plot, box plot. Okay, box and whisker is here. It's under histogram, right? Box and whisker, you do that, and there you go, you have a box plot. So now that's easy. And but a few things to notice. First of all, we talk about the upper whisker being the maximum value. But you can notice that in this case, there are some values even beyond the so-called maximum value, right? We'll come to that soon. And this means that this maximum value is not the actual maximum value in the data, but it is a maximum value that is estimated, okay? Before I go further, are there any questions about how this is done? Let me go to chat and see. Are there any questions about how this is done? Should be easy enough, right? Okay, so I don't see any question in chat. I assume that everybody gets it. Okay. And in the middle, there's x. There's a little x in the middle, and that indicates where the mean is. Okay. But you can see the box is colored, and you have median, okay, being depicted in the middle. And then you have the box. And you have a lower whisker as well. Okay. So that's how you do add a box plot, a simple box plot in using Excel. Again, this is not as detailed as histogram, but it provides you with some information, right? Key information about the distribution of the variable. Again, as I said before, that there's several different ways to plot the whiskers. Okay? So one way is to have the actual minimum and maximum values within the data set, empirical values. But the other is called 1.5 interquartile range criteria, which is also known as the Tukey method. So the minimum is quartile 1 minus 1.5 times interquartile range. So in this case, the length of the blue line here is 1.5 times the width of this square in the middle. Okay? So now anything beyond the maximum and below the minimum estimated this way are considered outliers. Quartiles, there are also many different ways to estimate the Q1 and Q3. And if you're familiar, they're actually in R, there are 9 different ways of estimating quartiles. So you don't have to know all of them. But just to be aware that the box plot that you see might have different ways of estimating these quartiles and whiskers. So just something that you should be aware of when viewing the box plot, okay? So let's take a 10-minute break. I'm going to, and at the same time, you can take attendance. If I go to menti.com, I'm going to go to the next slide. So you can take the attendance, and we'll be back at 2 o'clock. Stop recording.